Okay, so we're going to finish up section 7.2. And what we're going to look at first is how we can rewrite something that has trig in it without trig. What does without trig mean? Without sines, cosines, or tangents. Okay, no trig functions. So by the end of me going through this, you're going to be able to take a formula like that and rewrite it in a way that there's not going to be a sine or an inverse cosine in it anymore. We'll be able to get rid of it. And the whole key to this problem is kind of like some of the questions I was going over in the homework. You're going to start with the inner trig function, and we're going to draw a right triangle diagram. And usually we're going to know two sides. You might know opposite and adjacent, or adjacent and hypotenuse, but you're going to know two. And we'll use Pythagorean theorem to get the third one. Now, when I say inner trig function, inverse cosine, I would consider to be the inner function. I would consider sine to be the outer function. If the inner trig function has inverse trig, like some of the problems in the homework, we're going to rewrite that. The way we're going to rewrite it is to use regular trig. So that means canceling out the inverse trig function by using a regular trig function. The reason regular trig is helpful is because then you know two sides of a triangle and you can make a diagram, which is what I just mentioned right before. So as we go through this, keep in mind the Pythagorean theorem, because that's going to help you to figure out the third side that you don't know. So there's going to be a lot of square roots with this. Okay, Pythagorean theorem, most of the time answers don't come out nice. So we'll be working with square roots. Just remember, if you end up with a square root, don't leave it in the bottom of a fraction. You need to fix them. So we'll go through a couple examples of this process. And there isn't really anything you can do on the calculator with this, so I'm not going to get those out right now. If we get to a part where I think you need them, I'll take them out. All right, let's look at that first question. The sine of the inverse cosine of v. The letter they use here, that doesn't matter. Okay, that's not important. So it says write an algebraic expression for the formula that's right on the book. So first thing it said to do is start with the inner trig function. What's the inner trig function here? Yep.
Inverse cosine v.
Yep. We're going to forget about sine for now. We're going to come back to it, but we're not going to use the sine here till the very last step in the problem. We're going to focus everything on this inner trig function. And what did I say before? When you use inverse trig, you're always solving for what? When you do an inverse trig problem on the calculator and hit enter, the number that pops up on the screen represents something in a triangle. Yep. It represents an angle. I don't know what the angle is going to be here. I don't know v, so I'm never going to know the angle. But I know that when I do this problem out, what's inside the parentheses, it's going to equal some angle. In trig, when we don't know what the angle is, we usually use a Greek letter. So we're going to start by doing that. This is what's going to help us to set up a right triangle diagram. But when we want to set up a right triangle diagram, we don't really want to use inverse trig. We want to use What? Yeah? We want regular trig. So I want to rewrite this question in a way that has regular trig, not inverse trig. So, as the second step says, rewrite using regular trig. So how are we going to get rid of the inverse cosine? Yeah?
Cosine.
Yeah, we're going to take the regular cosine. The step I'm about to do, there is no multiplication in this step at all. It's like if I said to you to take the square root of 8. Just because you put the square root symbol next to that number, it doesn't mean you're multiplying here at all. This has nothing to do with multiplying a square root symbol times 8. That doesn't even make sense. So we're going to do the same thing here. We're going to put the cosine symbol there. That is what I'm taking the cosine of. The entire thing on the left and the entire thing on the right. Those cancel. Now I have this. I know a trig function now. So I want to draw a triangle, and I want to label the information that I can based on what I have written right there. Now, you need to remember what cosine is. What's the definition of cosine? Yep.
Was that one adjacent over hypotenuse?
That's adjacent over hypotenuse. Now, my formula for cosine doesn't have a fraction on the other side. Well, I need to make it a fraction. What can I put in the bottom that would make it a fraction? Yep, 1. So, there's your adjacent. There's your hypotenuse. Draw a triangle and label the adjacent and the hypotenuse exactly the way they're labeled right there. Okay, it doesn't matter where you put theta. Just make sure wherever you put it, the adjacent is v and the hypotenuse is 1. So that's most of our diagram. This part right here is what I just drew a diagram for. So what this problem is saying now is take the sine of your diagram, because we just drew this out. The sine of your diagram. What's the definition for sine? Yep.
Opposite over hypotenuse.
Opposite over hypotenuse. Well, I have hypotenuse. I do not have the opposite. So I could make up a letter temporarily. I'm going to erase that letter in a minute. But how am I going to figure out what this letter is based on these other two sides? Yeah? Yeah. And can you set up the Pythagorean theorem for me with those three things?
Yeah, x squared plus b squared equals
1 squared. Now solve that for x. You're going to have a formula right here for this side based off of the 1 and the v. So let's solve for x. So x squared is 1 minus v squared. So what's x? Yeah. Square root both sides. And there is nothing you can do to simplify that. That's as simple as that answer for x gets. So this side is the square root of 1 minus v squared. And the whole reason I found that side is because look what the question was asking. Take the sine of your diagram. Sine is opposite over hypotenuse. I needed the opposite. Okay. So what's the opposite here? Matt?
Square root of 1 minus b squared.
And what's the hypotenuse?
1.
1. So the answer to this question is the sine of what I just drew. It's the square root of 1 minus v squared divided by 1. And that's the answer. This whole thing equals this. Let's try a number for v. Give me something between -1 and 1, otherwise it won't work. What's a number between -1 and 1? Pick any random number you want. Yeah?
0.5.
0.5. Okay, so if I take the sine of the inverse cosine of 0.5, that's what I get, 0.866. Now plug 0.5 in over here and see if you get the same thing. The square root of 1 minus, what did you say, 0.5?
Yep.
0.5 squared. It just filled in 0.5. I'm just a random number to check. 0.866. So that shows you, it doesn't prove it. The algebra proves it. But that's an example showing you that this formula will give you the exact same result as that formula. What's the difference? This one has trig. This one does not. Yeah.
Is the square root of 1 squared 1, or is it the square root of 1?
The square root of 1 squared?
Yeah.
1.
It's just 1.
Yeah. Yeah. Any question on that? Just thinking about your question. So you're asking about this, square root of 1 squared. So if it depends if you're considering the negatives or not. So if you do this out, and you think of, well, let's follow order of operations, square the 1 first. You get the square root of 1. And then if we're talking about positive and negative answers, then I guess you could write 1 or -1. Because if you take the square root of 1, you're asking what number times itself is 1. 1 times 1? -1 times -1. Yeah. So 1 or -1. A lot of times, though, if we're looking for positives and negatives, they put this symbol in front of the root, so that way you know you're looking for both. Depends on the problem. But, all right, let's try another one of those. Okay. So on the left, I've got a formula with trig in it. On the right, I have a formula, well, that I don't know yet. But my goal is to end up with a formula without trig. Okay, which function do we start with? The outside or the inside? Yeah, the inside. And we know that when you do inverse trig, you're solving for an angle. So what should I set the inside function equal to? Yep, theta. And now I want to draw a right triangle diagram for this. I can jump right to the diagram in my head by looking at that. But if you can't, it helps to rewrite this with regular trig. So how would you get rid of the inverse sign? Yep.
You would take the regular sign on both sides?
Yep, and the verb he used there was perfect. He said take. There is no multiplication in this entire problem. So you're going to take the sign of both sides. Sometimes they use a bracket here just to make this to distinguish it from the other parenthesis. What I do is I just make my other parenthesis larger so you can tell, that's what it is. So we're going to take the sign of the left and then take the sign of what's on the right. Regular sign and inverse sign cancel out. And you get v equals sine theta. Now, we're going to have to think of sine as a trig function, that's something over something. So I need a number in the bottom on this other side. What could I put in the bottom? Yep. 1. Now, draw your diagram. And make sure your diagram represents what this says. The sine is equal to the opposite over the hypotenuse. Opposite over hypotenuse. This is exactly the same diagram as the last problem. one side had a V, the hypotenuse was a 1. One side had a V, and the hypotenuse was a 1. So the third side is going to be exactly the same again. It's in a different spot, but they're just switched. So it's going to be the square root of 1 minus V squared. Now, once you draw your diagram, go back up to the original problem. What I just underlined in red, we made a diagram for that. They want me to do the tangent of my diagram. What is tangent? Yep.
Opposite over adjacent.
Opposite over adjacent. So V over the square root of 1 minus V squared. So that is the answer without any trig in it, but we've left something there we shouldn't. What do we have to get rid of?
Square root from the bottom.
Yeah. And the way you get rid of the square root on the bottom is you multiply the top and the bottom by the square root. We do that a lot when it's just a number. We're doing pretty much the same thing. So the top, you can't really do much with it. It's just V times the square root of 1 minus V squared. But what does the bottom turn into? Yeah.
1 minus V squared.
That's the whole point of doing it. It turns into what you have there already, but the root is gone. Okay, and I'm not going to try an example on that, but if you pick a number between -1 and 1, and you plug it in for V and get the answer here, and then you plug it in for V and get the answer there, you will get exactly the same thing. And again, the difference, the formula on the left is a trig formula. The formula on the right is algebraic. There's no trig in that at all. Okay. Any question on that?
How do we get V over the square root of 1 minus V squared?
How did we get
Like the red.
this one? So this came from the tangent. This was the opposite, and that was the adjacent.
Okay.
So this part on the outside, you don't end up using till the very end of the problem. Let's try... All right, let's try this one. Okay, same type of problem again, but this time, when you go to label your sides in your triangle, you have actual numbers. You don't have a V and a 1. You have a 1 and a 2. So everything in this problem is going to be numeric. And if you try to type this in on the calculator, the cosine of the inverse tangent of a half, you can get an answer, bless you, but the problem is it's a decimal. On a question like this, it's going to ask for the exact answer, and the calculator can't do that.
Wait, wasn't it just regular cosine?
Oh, did I do the wrong one? Oh, thanks. So again, it's still a decimal. That calculator cannot give you an exact answer for it. We'll put it off to the side, and we can check our answer we get and see if it comes out to 0.89, and then we know we did it right. Okay, so which trig function do we want to start with? Yep.
The inside one.
Inside one. What do we set it equal to? Yep.
Theta.
Set it equal to theta. And then to think about this in terms of a right triangle, what are we going to take on each side? Yep. Take the tangent. And take the tangent. When you take the tangent on each side, what happens on the left? Cancels out the tangents. And now you have 1/2 equals the tangent. So now draw your diagram. Put theta. Can someone remind me, what's the formula for tangent? What over what?
Opposite over adjacent.
Opposite over adjacent. Opposite over adjacent. So I do not need to use any letters when I label it this time. If I use Pythagorean theorem, My third side is going to be the square root of something. Yeah?
Square root of 3.
It's going to be square root of
Or was it 2?
5.
5.
Oh, 5.
Square this, you get 2. Square that, you get 1. Well, try again. Square this, you get 4. Square that, you get 1. 4 plus 1 is 5.
Wait, which one was the 1, 2 square root of 3?
That's a 30, 60, 90 right triangle.
Oh, is that the hypotenuse is a 2? Like opposites 1?
Oh, yeah. If the hypotenuse was a 2, then that would have been a square root of 3.
Okay.
Yeah. Okay, so now we've got our diagram, which represents this. Now we want this, the cosine of my diagram. Cosine is what over what? Yeah? Adjacent over hypotenuse. 2 over the square root of 5. Which, when I fix that so the root's not in the bottom, what do I get?
2 square root of 500.
And the nice thing about this is it's very easy to check the answer because it should come out to 0.89. Except 2 root 5 over 5 is exact, 0.89 is not. Let's try it. 2 root 5 over 5. Perfect. So we know we got the right answer.
Are you saying 0.89 isn't exact because it goes longer than that?
Oh yeah, this just keeps going forever. And I can prove it keeps going forever because I know the square root of 5 goes on forever. And there's no way to write square root of 5 as a fraction. It's impossible.
So if we weren't doing a quiz and they asked for an exact answer, that's what they're looking for.
Exact answer, you've got to write this.
Gotcha.
Even if you put 0.894427191, that's not exact.
Yeah.
You've given me a lot of numbers, but it's not exact. Okay, so any question on that? That's probably the easiest type where you have a number on the inside. Then you don't have to deal with any letters like the first two. That's kind of another one. It's pretty much the same type. Does anybody want to see another one of that type? I mean, the fast way is when you draw your triangle, you're going to have theta. The opposite is 1. The hypotenuse is 2. And there's what you were just talking about, square root of 3. And then take the cosine, adjacent over hypotenuse. The answer is root 3 over 2. So it's really the same as the last one. All right, so let's try something a little different. So remember, trig equations are periodic. That means that they keep repeating themselves. So let's say I had a trig equation like this, and I asked you, where does it equal 0.4? Well, you'd put the trig equation in y1, you'd put 0.4 in y2, and you'd get something like this. How many times is the wave in the line going to cross? Yeah?
Like indefinitely?
Right, it's going to cross infinitely many times. But we know that this answer is really the same as that one, which is the same as that one, which is the same as that one. How far is it from this answer to that answer in general? Yeah?
1 period.
1 period, whatever the period is. So once you find one answer to the problem, all you have to do is tell me that that answer repeats forever. And not only does it repeat to the right, I could have also drawn it repeating to the left. But that answer in green repeats forever. And then you'd have this answer. And all those answers in blue are the same answer. You just have to find the first one and tell me that it's going to keep repeating every single period. So if you wanted to get this answer, say right there, and you had this answer. How many periods away is that answer from that answer? Yeah,
Would be 3.
it'd be 3. So you would have to add 3 copies of the period to get that answer if you knew that one. What if I wanted this one? How many copies of the period would I have to add to this answer to get that answer? Yep. 2. The idea is you can add any number copies to the first answer, and it'll give you an answer later on. If you add 50 copies, you get the answer 50 periods later. If you subtract 5 copies, you get the answer 5 periods earlier. You just have to find one answer, and then tell me that it repeats. So I think we mentioned this before, but the way that your answers are going to look is something like x equals, and then you're going to have to use second calc intersect to get what goes in that box. And then you put plus the period times n. This represents adding any number multiple of the period to the first answer you found. 1 copy, 2 copies, 3 copies, because this number has to be an integer. So let's say it was 5. 5 times the period would add 5 copies of the period. If it was 7, 7 times the period would add 7 copies to it. But this is the idea that represents the answer repeating forever. Now, you might look at that and say, well, yeah, but you only put plus. I thought you said the answer is going to repeat forever in both directions. Well, remember, integers can be negative. So if you plug in -2, -2 times the period means -2 copies of the period added to this. Well, if you add -2 copies to it, that brings you to the left instead of to the right. So it's very important that you write your answers in this format if they say find all solutions. So you find the intersect and you put plus the period times n. We might, I don't know if we mentioned that before. We might have. Did we talk about that before? Yeah.
When you say a reciprocal identities, are you talking about like cosecant, secant?
Yeah, so if you have to type in something like cotangent, secant, or cosecant, you don't have a button for those. So you're going to have to type in like 1 over tangent for cotangent. Yeah. Let's try a couple examples and that'll be it. We are going to do one that's a reciprocal in a minute. So we'll try that. Okay, so sine of x equals 0.6. The directions say to find all solutions. Well, we know if there's one, then there's infinitely many. Because think of what sine looks like. It's a wave. If you draw a horizontal line and it hits the wave once, it hits it forever, over and over. So, to figure this out, what would I put in y1? Yep.
Sine of x.
Yep. Put in sine of x. And what would I put in y2? Yep. 0.6. And this is going to pretty much look exactly like what I did right here. That's exactly what this one is. Okay, let's graph it. I'm going to do zoom 7 because that's going to set my window for a trig problem. We don't want to do zoom 6. Okay. And we want to basically think of how many different answers we're getting there. Now, I know there's infinitely many, but I guess my question is, how many times are we going to have to do second calc intersect? Yeah?
2 times.
2 times. So think of it like this. That's one cycle. Find all the answers in that cycle, and then tell me that they repeat forever. So let's find those two. Now, technically, you could find two answers in any cycle, because once I know two answers and you tell me they repeat forever, it's kind of the same thing. I usually do the first two positive answers most of the time. So let's do that. Second calc intersect. Okay, so the first one is 0.64. Okay, we're not done with that yet. And the second one is second calc intersect 2.50. Now, if you write that, you have not answered this. You've told me two answers to the problem. But what do I have to put on the end of each one of these to represent all the solutions? Start with being very general. You don't have to say anything specific in terms of a number here. Yeah?
Like the plus period times n.
You need to put plus period times n. But you can't write the word period. You have to put the period to this problem. So what I'm asking is, what's the period of the sine function? Yep,
2 pi.
it's 2 pi. If you don't remember the formula for that, the formula to calculate it is 2 pi over b. In this case, b is 1. So the period in this problem is 2 pi. So plus any number of multiples of 2 pi to the first answer, and plus any number of multiples of 2 pi to the second answer. And that represents all the answers to the problem. And if you're still not quite sure what that means, here's kind of something concrete. If you let n equal 1, it would add one multiple of 2 pi to that answer, which would be that answer right there. If you add one multiple of 2 pi to this answer, it would be that answer right there. Any question on that? Right, let's try a cotangent. Before we type it in, let's just see if we can figure out the period. So for sine, cosine, secant, and cosecant, we use the formula 2 pi over b. We don't use that formula to figure out the period of tangent and cotangent. Does anybody remember what the formula is for the period of tangent and cotangent? Yeah?
Pi over b.
It's pi over b. And remember, b is the number that's in front of the x. What number is in front of the x in this case? 1. So the period here would be pi. Yep. Period is pi. Right. So keep that in mind when we put our answer. We're going to put that on the end of it. All right, now I need to type all this in. What am I going to put in y1? Yeah?
The cotangent of x, but I forget how to type it in.
Yep.
Is it 1 divided by tangent?
Right. To type that in, we have to use the reciprocal identity, which basically says if you flip tangent, you get cotangent. So flip the tangent. And what about in y2? Yep. 2.5. And if we want to make life a little simpler, we could set the window so that it is only one period wide. Then we're not looking at multiple places we would have to find intersections. If it confuses you to look at all of those. what would be the simplest way to set this window so that it is exactly 1 period wide, and your period is pi?
Set the x min to 0 and then x max to pi.
Yeah.
And then add the y min to 1 and then y max to, or y min to -1 and then y max to 1, or would that not matter?
Well, think about what we're graphing. We're graphing a cotangent function.
Oh yeah, that's right.
We're not graphing a sine or a cosine, which would fit in the window you just mentioned.
Yeah.
Cotangent goes up and down forever, so I would leave it -4 to 4.
Okay.
Even if it was sine and cosine, you really could leave it -4 to 4.
Okay.
But the important thing is, if you want to try to not get as confused about where the intersection is on the screen, set your window to 1 cycle. Okay? So 0 to pi. That's exactly 1 cycle of cotangent. And that would repeat over and over. How many answers do we get to this problem per cycle? I mean, there are infinitely many answers, but per cycle, 1. In the last problem, it was 2 per cycle. So this time, the only answer we're going to have is going to look something like this. Tell me the first answer, and then tell me that it repeats forever, every period. Okay, so second calc intersect. We're only looking for 1, so you really don't have to be too careful where you put it. Just hit enter, and you get 0.38. That's an 8. That's it. Any question on that? Okay, so really 2 big things we looked at today. Taking a formula that has trig, writing it without trig, and using the calculator to get answers to trig equations. Okay, in 7.3, I think we're going to do more finding answers to trig equations. So we'll look at that a little bit more tomorrow. Okay, so that's the homework for tonight. It's on 394. Same section as last night. So 37, 38, 41, 42. And 45 to 47, 49 to 53. Let me double check that because I may have to take off a question. 37, 38's okay. 39, 41. Actually, it might be okay. 2. That's actually, it's okay.